A four-stroke engine is an internal combustion engine in which the piston completes four separate strokes while turning a crankshaft. A stroke refers to the full travel of the piston along the cylinder, in either direction. The four separate strokes are termed intake. This stroke of the piston begins at top dead center and ends at bottom dead center. In this stroke, the intake valve must be in the open position while the piston pulls an air-fuel mixture into the cylinder by producing vacuum pressure into the cylinder through its downward motion. Compression. This stroke begins at BDC, or just at the end of the suction stroke, and ends at TDC. In this stroke, the piston compresses the air-fuel mixture in preparation for ignition during the power stroke. Both the intake and exhaust valves are closed during this stage. Combustion. This is the start of the second revolution of the four-stroke cycle. At this point, the crankshaft has completed a full 360-degree revolution. While the piston is at TDC, the compressed air-fuel mixture is ignited by a spark plug or by heat generated by high compression, forcefully returning the piston to BDC. This stroke produces mechanical work from the engine to turn the crankshaft. Exhaust. During the exhaust stroke, the piston once again returns from BDC to TDC while the exhaust valve is open. This action expels the spent air-fuel mixture through the exhaust valve. History. Otto cycle. Nicolaus August Otto as a young man was a traveling salesman for a grocery concern. In his travels he encountered the internal combustion engine built in Paris by Belgian expatriate Jean-Joseph Etienne Lenoir. In 1860, Lenoir successfully created a double-acting engine that ran on illuminating gas at 4% efficiency. The 18-liter Lenoir engine produced only 2 horsepower. The Lenoir engine ran on illuminating gas made from coal, which had been developed in Paris by Philippe Laban. In testing a replica of the Lenoir engine in 1861, Otto became aware of the effects of compression on the fuel charge. In 1862, Otto attempted to produce an engine to improve on the poor efficiency and reliability of the Lenoir engine. He tried to create an engine that would compress the fuel mixture prior to ignition, but failed as that engine would run no more than a few minutes prior to its destruction. Many other engineers were trying to solve the problem, with no success. In 1864, Otto and Eugene Langen founded the first internal combustion engine production company, NAR Otto and CIE. Otto and CIE succeeded in creating a successful atmospheric engine that same year. The factory ran out of space and was moved to the town of Deutz, Germany in 1869, where the company was renamed to Deutz Gasmotorenfabrik AG. In 1872, Gottlieb Daimler was technical director and Wilhelm Maybach was the head of engine design. Daimler was a gunsmith who had worked on the Lenoir engine. By 1876, Otto and Langen succeeded in creating the first internal combustion engine that compressed the fuel mixture prior to combustion for far higher efficiency than any engine created to this time. Daimler and Maybach left their employ at Otto and CIE and developed the first high-speed Otto engine in 1883. In 1885, they produced the first automobile to be equipped with an Otto engine. The Daimler Reitwagen used a hot tube ignition system and the fuel known as Ligroin to become the world's first vehicle powered by an internal combustion engine. It used a four-stroke engine based on Otto's design. The following year, Carl Benz produced a four-stroke engined automobile that is regarded as the first car. In 1884, Otto's company, then known as Gasmotorenfabrik Deutz, developed electric ignition and the carburetor. In 1890, Daimler and Maybach formed a company known as Daimler Motor and Gesellschaft. Today, that company is Daimler-Benz. Atkinson cycle. The Atkinson cycle engine is a type of single-stroke internal combustion engine invented by James Atkinson in 1882. The Atkinson cycle is designed to provide efficiency at the expense of power density, and is used in some modern hybrid electric applications. The original Atkinson cycle piston engine allowed the intake, compression, power, and exhaust strokes of the four-stroke cycle to occur in a single turn of the crankshaft and was designed to avoid infringing certain patents covering Otto cycle engines. Due to the unique crankshaft design of the Atkinson, its expansion ratio can differ from its compression ratio, and, with a power stroke longer than its compression stroke, the engine can achieve greater thermal efficiency than a traditional piston engine. While Atkinson's original design is no more than a historical curiosity, many modern engines use unconventional valve timing to produce the effect of a shorter compression stroke, longer power stroke, thus realizing the fuel economy improvements the Atkinson cycle can provide. Diesel cycle. The diesel engine is a technical refinement of the 1876 Otto cycle engine, where Otto had realized in 1861 that the efficiency of the engine could be increased by first compressing the fuel mixture prior to its ignition. Rudolf Diesel wanted to develop a more efficient type of engine that could run on much heavier fuel. The Lenoir, Otto atmospheric, and Otto compression engines were designed to run on illuminating gas. With the same motivation as Otto, Diesel wanted to create an engine that would give small industrial concerns their own power source to enable them to compete against larger companies, and like Otto to get away from the requirement to be tied to a municipal fuel supply. Like Otto, it took more than a decade to produce the high-compression engine that could self-ignite fuel sprayed into the cylinder. Diesel used an air spray combined with fuel in his first engine. During initial development, one of the engines burst, nearly killing him. He persisted and finally created an engine in 1893. The high-compression engine, which ignites its fuel by the heat of compression, is now called the diesel engine, whether a four-stroke or two-stroke design. The four-stroke diesel engine has been used in the majority of heavy-duty applications for many decades. It uses a heavy fuel containing more energy and requiring less refinement to produce. The most efficient Otto cycle engines run near 30% efficiency. Thermodynamic analysis. The thermodynamic analysis of the actual four-stroke or two-stroke cycles is not a simple task. However, the analysis can be simplified significantly if fair standard assumptions are utilized. The resulting cycle, which closely resembles the actual operating conditions, is the Otto cycle. During the normal operation of the engine, as the fuel mixture is being compressed, an electric arc is created to ignite the fuel. At low RPM this occurs close to TDC. As engine RPM rises, the spark point is moved earlier in the cycle so that the fuel charge can be ignited while it is still being compressed. We can see this advantage reflected in the various Otto engines designs. The atmospheric engine operated at 12% efficiency. The compressed charge engine had an operating efficiency of 30%. Fuel considerations. The problem with compressed charge engines is that the temperature rise of the compressed charge can cause pre-ignition. If this occurs at the wrong time and is too energetic, it can damage the engine. Different fractions of petroleum have widely varying flash points. This must be taken into account in engine and fuel design. The tendency for the compressed fuel mixture to ignite early is limited by the chemical composition of the fuel. There are several grades of fuel to accommodate differing performance levels of engines. The fuel is altered to change its self-ignition temperature. There are several ways to do this. As engines are designed with higher compression ratios, the result is that pre-ignition is much more likely to occur since the fuel mixture is compressed to a high temperature prior to deliberate ignition. The high temperature more effectively evaporates fuel such as gasoline, which increases the efficiency of the compression engine. Higher compression ratios also mean that the distance that the piston can push to produce power is greater. The octane rating of a given fuel is a measure of the fuel's resistance to self-ignition. A fuel with a higher numerical octane rating allows for a higher compression ratio, which extracts more energy from the fuel and more effectively converts that energy into useful work while at the same time preventing engine damage from pre-ignition. High-octane fuel is also more expensive. Diesel engines, by their nature, do not have concerns with pre-ignition. They have a concern with whether or not combustion can be started. The description of how likely diesel fuel is to ignite is called the cetane rating. Because diesel fuels are of low volatility, they can be very hard to start when cold. Various techniques are used to start a cold diesel engine, the most common being the use of a glow plug. Design and engineering principles. Power output limitations. The maximum amount of power generated by an engine is determined by the maximum amount of air ingested. The amount of power generated by a piston engine is related to its size, whether it is a two-stroke or four-stroke design, volumetric efficiency, losses, air-to-fuel ratio, the calorific value of the fuel, oxygen content of the air, and speed. The speed is ultimately limited by material strength and lubrication. Valves, pistons and connecting rods suffer severe acceleration forces. At high engine speed, physical breakage and piston ring flutter can occur, resulting in power loss or even engine destruction. Piston ring flutter occurs when the rings oscillate vertically within the piston grooves they reside in. Ring flutter compromises the seal between the ring and the cylinder wall, which causes a loss of cylinder pressure and power. If an engine spins too quickly, valve springs cannot act quickly enough to close the valves. This is commonly referred to as valve float, and it can result in piston-to-valve contact, severely damaging the engine. At high speeds, the lubrication of piston-cylinder wall interface tends to break down. This limits the piston speed for industrial engines to about 10 meters per second. Intake, exhaust port flow. The output power of an engine is dependent on the ability of intake and exhaust matter to move quickly through valve ports, typically located in the cylinder head. To increase an engine's output power, irregularities in the intake and exhaust paths, such as casting flaws, can be removed, and, with the aid of an air flow bench, the radii of valve port turns and valve seat configuration can be modified to reduce resistance. This process is called porting, and it can be done by hand or with a CNC machine. Supercharging. One way to increase engine power is to force more air into the cylinder so that more power can be produced from each power stroke. This can be done using some type of air compression device known as a supercharger, which can be powered by the engine crankshaft. Supercharging increases the power output limits of an internal combustion engine relative to its displacement. Most commonly, the supercharger is always running, but there have been designs that allow it to be cut out or run at varying speeds. Mechanically driven supercharging has the disadvantage that some of the output power is used to drive the supercharger, while power is wasted in the high-pressure exhaust, as the air has been compressed twice and then gains more potential volume in the combustion, but it is only expanded in one stage. Turbocharging. A turbocharger is a supercharger that is driven by the engine's exhaust gases by means of a turbine. It consists of a two-piece, high-speed turbine assembly with one side that compresses the intake air, and the other side that is powered by the exhaust gas outflow. When idling, and at low to moderate speed, results. The turbine produces little power from the small exhaust volume. The turbocharger has little effect and the engine operates nearly in a naturally aspirated manner. When much more power output is required, the engine speed and throttle opening are increased until the exhaust gases are sufficient to spool up the turbocharger's turbine to start compressing much more air than normal into the intake manifold. Turbocharging allows for more efficient engine operation because it is driven by exhaust pressure that would otherwise be wasted. But there is a design limitation known as turbo lag. The increased engine power is not immediately available due to the need to sharply increase engine RPM, to build up pressure and to spin up the turbo, before the turbo starts to do any useful air compression. The increased intake volume causes increased exhaust and spins the turbo faster, and so forth until steady high-power operation is reached. Another difficulty is that the higher exhaust pressure causes the exhaust gas to transfer more of its heat to the mechanical parts of the engine. Rod and piston to stroke ratio. The rod to stroke ratio is the ratio of the length of the connecting rod to the length of the piston stroke. A longer rod reduces sidewise pressure of the piston on the cylinder wall and the stress forces, increasing engine life. It also increases the cost and engine height and weight. A square engine is an engine with a bore diameter equal to its stroke length. An engine where the bore diameter is larger than its stroke length is an over-square engine. Conversely, an engine with a bore diameter that is smaller than its stroke length is an under-square engine. Valve train. The valves are typically operated by a camshaft rotating at half the speed of the crankshaft. It has a series of cams along its length, each designed to open a valve during the appropriate part of an intake or exhaust stroke. A tappet between valve and cam is a contact surface on which the cam slides to open the valve. Many engines use one or more camshafts above a row of cylinders, as in the illustration, in which each cam directly actuates a valve through a flat tappet. In other engine designs, the camshaft is in the crankcase, in which case each cam usually contacts a push rod, which contacts a rocker arm that opens a valve, or in case of a flathead engine a push rod is not necessary. The overhead cam design typically allows higher engine speeds because it provides the most direct path between cam and valve. Valve clearance. Valve clearance refers to the small gap between a valve lifter and a valve stem that ensures that the valve completely closes. On engines with mechanical valve adjustment, excessive clearance causes noise from the valve train. A too small valve clearance can result in the valves not closing properly. This results in a loss of performance and possibly overheating of exhaust valves. Typically, the clearance must be readjusted each 20,000 miles with a feeler gauge. Most modern production engines use hydraulic lifters to automatically compensate for valve train component wear. Dirty engine oil may cause lifter failure. Energy balance. Otto engines are about 30% efficient. In other words, 30% of the energy generated by combustion is converted into useful rotational energy at the output shaft of the engine, while the remainder being losses due to waste heat, friction and engine accessories. There are a number of ways to recover some of the energy lost to waste heat. The use of a turbocharger in diesel engines is very effective by boosting incoming air pressure and in effect provides the same increase in performance as having more displacement. The Mack Truck Company, decades ago, developed a turbine system that converted waste heat into kinetic energy that it fed back into the engine's transmission. In 2005, BMW announced the development of the turbo steamer, a two-stage heat recovery system similar to the Mack system that recovers 80% of the energy in the exhaust gas and raises the efficiency of an Otto engine by 15%. By contrast, a six-stroke engine may reduce fuel consumption by as much as 40%. Modern engines are often intentionally built to be slightly less efficient than they could otherwise be. This is necessarily for emission controls such as exhaust gas recirculation and catalytic converters that reduce smog and other atmospheric pollutants. Reductions in efficiency may be counteracted with an engine control unit using lean burn techniques. In the United States, the corporate average fuel economy mandates that vehicles must achieve an average of 34.9 mpg US compared to the current standard of 25 mpg US. As automakers look to meet these standards by 2016, new ways of engineering the traditional internal combustion engine have to be considered. Some potential solutions to increase fuel efficiency to meet new mandates include firing after the piston is farthest from the crankshaft, known as top dead center, and applying the millicycle. Together, this redesign could significantly reduce fuel consumption and NOx emissions.